velice oznakování. Choosing handbook.
So, the first theme today, very simple in some sense, is to recall how you can go from certain vector spaces so let me say vector space constructions you know what I mean in a minute, of course, to vector bundle construction. Now there may be even a way to think about this. I'm going to draw a crazy picture like my usual pictures are crazy. Here is a vector space, V, but I realize this or regard this as a vector bundle over a point. Well, this one vector space is just a bundle, well, it's not much of a bundle, just one vector space over a point. But that's a good way of thinking. It's what we think in mathematics. We have phenomena or structures that are rigid, but then we move them. We move parameters. Right? Also in physics, we're moving parameters all the time. So that is a vector space. Say over the complex of real numbers. And over a point. And now over a manifold, well, we have a vector space over that point, but we have vector spaces over every point. So instead of a vector space over one point, which is just a vector space, this is a vector space over a point. This is a vector bundle over a manifold. So that is the intuition that I have. By the way, I always know there's zero here. There's always have the zero section, right? Now recall some ideas that we've talked before. So I'm going to talk about constructions. Just a few to give you some ideas, and then you can do the rest yourself. Constructions. Let's say at the vector space level, and at the vector bundle level. Say that this is for short, let me just write bundle. Maybe I'll make a table in some sense. So one kind of, let's just start making some amusing constructions. If you have a vector space, everybody learns if you have a vector space, then you can go to the dual space. You even see already here that if you have the usual representation here of GLV, so just the linear transformations on the vectors, maybe you think of it as a matrix if we have a frame. Here you have the usual transformations on V star, and there's a way of going from here to here. Remember we talked about it. Here, say, if you think of this as a matrix, you may, if you like, A of a function, you have to say what happened. You got another function applied to x is f of A inverse of that. So when you go from here to here, you learn how the transformations change. Here you have the usual action of linear function, linear operators. Here you have the dual, we say dual representation. In a matrix, this will be A inverse transpose. And if you write it in the usual matrix action, A inverse transpose, just the matrix A. Well, the same thing happens here. If we go into a vector bundle, since it's going from the bundle, the vector space to the dual space, you have a vector bundle over a manifold. Then you could go to the dual bundle of the manifold. What does that mean? Well, that means you've replaced every fiber that was once a fiber over a point. For example, here's a point P. You have the fiber EP over that point. You replace every fiber by the dual space to that fiber. That space, every fiber is replaced by the dual space to that fiber. Right? The structure group, the general fiber is, of course, for the bundle E. Maybe I should write here E. The general fiber for the bundle E is Rn. And the general fiber is still Rn, but I'm going to write it in a better way. It is the dual of Rn. And the structure group here is GLNR, acting in the usual way. And the structure group here is GLNR. It's linear, it's a vector bundle, but acting by the dual representation. Now what in the devil does that mean at the bundle level? It means that if you have a frame change, right? Frame change here in E is given by G alpha beta in GLNR, and frame change here, well, it's just whatever it is, G alpha beta. These are matrices now, so this is probably, if I get my numbers right, this is G alpha beta inverse transpose. Okay. This is how the frames change if they are vectors, and this is how the frames change if they are covectors, some people say. Dual vectors, or we say linear functions. Well, it's completely clear if this thing changes frames in a smooth way, then this thing changes frames in a smooth way. So this means that if you have a vector bundle here, E, with a smooth vector bundle, then this vector bundle here is also a smooth vector bundle. It's just a different vector bundle, because the frames are changing in a different way. This is a completely different vector bundle. Get it in your heads. Everybody says, in Mickey Mouse mathematics, any two vector spaces of the same dimension are the same. That, of course, is nonsense. They are at least isomorphic, right? They're at least isomorphic, so that's not nonsense. But these vector bundles, E and E dual, will almost never be the same vector bundle, and never be isomorphic, essentially never. I will talk about that and keep that in mind. So that's what I want to show you in my table here. You start with a process which goes from V to V star. You have the same process in bundles. You go from the bundle to the dual bundle. Okay. Well, you can have fun staying up all night, and then occasionally you try to listen to the elections in the United States and see that my man won. And then you go back to interesting mathematics because you have to do something more, less frustrating. And you have many things on this side. For example, you have two vector spaces. and you go to the direct sum of these two vector spaces. You have two vector spaces, you go to the tensor product of these vector spaces. You have one vector space, you go to the k-fold tensor product of this thing, and if you're excitable, you even go to the full tensor product of this thing. If you have one vector space, you might want to go to the k-fold symmetric product of that vector space, or you might want to go to the k-fold alternating product of that vector space. This is what I've talked about. You missed it, but you can read my last, go to my last video. It's not bad, actually. I showed my wife, she liked it. So, you see, you have a construction on the left-hand side, and you better believe me, you can just take it right over to the right-hand side. You have two vector bundles. I'm not even going to write it. You have two vector bundles with fibers E, P, and FP. Right? You replace this fiber EP and FP with the direct sum of EP and FP. The structure group on EP acts on GL, whatever it is here, and the other on here, so it's the product of the two structure groups. The same thing here. Here, quite frankly, also you have V, and you have all these tensors, and the structure group is just, I like to say it's only two possibilities. Either the structure group acts on everyone differently, so it's GLNR times GLNR times GLNR. You see what I'm saying? Each factor individually, or I say diagonally. So, in other words, one possible action here would be a tensor V1 through the, I don't know, K tensor, could be acted upon by an element of GLNR. One action that I like is the diagonal action. One reason I like the diagonal action is if you have a symmetric tensor, that only the diagonal action makes sense. Because don't forget, I mean, you're turning everything around and so on, the same thing here. So really, I usually quite often think of this diagonal action as the action of the structure group. So I think I will give you a homework exercise, elementary homework exercise, to work out one of these things, but you see the general philosophy. If there's any construction you can make with vector spaces, you can just do the same thing. Somehow, all you're doing is you're doing the same thing, but with a parameter. But don't forget, these parameters are glued together. See, this thing it's trivial, it's locally trivial, so it's trivial here, and it's trivial here, but they're glued together by the structure group. So it's a question of how the structure group is doing things. And for example, here on these tensors, particularly for these symmetric and alternating tensors, I prefer this diagonal action. Okay. Now I will tell you the secret. If you want to, at the same time, win all possible prizes, Nobel Prize several times, and in mathematics, Fields Medal several times, and Wolf Prize many times, and Abel Prize many times, and so on. I will tell you how to do it. I will now tell you how to do it. Well, it's very easy. You start with manifold M, and your mother asks you, what's the most interesting thing connected with that? And you say, tangent bundle. Your mother says, what's the devil is that thing? And you say, well, look, I had one vector space over a point, that's just a tangent space. Now I look at all vector spaces over all points, and that's the tangent bundle. And it's locally trivial, and the gluing goes by the structure group GLNR. And it goes like this. You just have to write down a local frame. And a local frame looks like this. Fi, local frame, a basis, local frame. functional basis? Well, it's just whatever spans, say, over U alpha. It's this order basis here, local frame on the tangent plane. Okay? And if I write something in one frame or another, I have to check what the frame change is. Right? That's the whole point here. I have to check what the frame change is. So frame change from this frame to this frame, say. That's going to be some frame change, which is either Jacobian or Jacobian transpose inverse. It's a question of what is the Jacobian. You understand what I mean? A Jacobian is a matrix, and I don't know, some guy, Jacobi was a mathematician in Berlin, and in the 19th century, early part of it, I guess. And I don't know if he knew what a Jacobian was. I'm not so sure. Right. But somebody at some time said that a gradient vector is a column vector. Now we're going to ask Professor Schub what a gradient vector is in physics. Is it a column vector or a row vector for you?
Column vector, certainly.
Pardon?
Column vector.
For me too. Okay. So as you know, we're now going to, Jacobi probably didn't get onto this, but we're going to fix what a Jacobian is. If a Jacobian is a column vector, which a gradient is a column vector, then a mapping is given by, say, a mapping from Rn to Rn. It's F1, F2, F3, F4, F5, F6 through Fn. And the Jacobian is gradient F1, gradient F2, gradient F3, gradient F4. It's the operator that is determined by the gradients of the individual coefficients of the function. I think you agree with that, right? That we should take as a Jacobian. And I think probably here, if you look, this thing transforms by the Jacobian transpose inverse. And even the physics notation, I think you will concur with this, proves that, because physics people talk about covariant vectors and contravariant vectors all the time. Mathematicians don't know what the devil that means. But covariant vectors transform good. If you're an American, you say covariance is good, and contravariance is the obvious. So good is the Jacobian, and contravariant is Jacobian transform inverse. And I learned that covariant vectors are, in fact, in the dual. So covariant vectors are functionals. They're in V star. So covariant vectors, I think, are not tangent vectors. They are one forms, I think. So the transformation here will be contravariant, and I think that will be Jacobian transpose inverse. And if you do the same thing on the dual frame, it will be the other way around. Now, I probably, everything I said was probably wrong. So that's the tangent. This is some Jacobian. I'll just write Jacobi here. Jacobi. And that's the smooth change of frame, and that's that kind of whatever it is. And your mother says, okay, why is that good? And you say, well, the reason that's good is that if you take this bundle and you draw a picture of it and you put in the zero section, that if a section of that bundle, we've talked about this, if you write a section of that bundle is a vector field. Section of that bundle is a vector field. We know that. Because vector fields locally look like they should look like in this basis, and they so a section of this thing, section of this is a vector field. If you don't believe me, then check it locally. Locally in a frame, S is equal in a frame to Fi, or I'll emphasize ddx alpha I in a local frame, and this transforms correctly. Right? In a local frame, say over here, you write it down this frame, the vector field is exactly a first order linear differential operator. That's it, basta. And the fact that these things glue together with the structure group is the fact that it's a globally defined vector. So our lingo, our notation is that these are sections of the vector bundle, of the tangent bundle. That's what this vector space is, and this is simply the vector bundle on it, vector field on it. So your mother's very happy with you. You've told her everything. Each fiber is the tangent space. These things put together smoothly. They're locally trivial. You can write down sections locally. They're vector field. This is very good. And when you see that picture, how many zeros does that vector field have in my picture? 3. Good. 3 zeros. No, you should get used to this. No, I'm serious. It's very important to get used to a picture. You might have another vector field quite often. You see, I've drawn this vector field as a section. It's transversal to the zero section, so the multiplicity of the zero is 1. If I would have another interesting vector field, well, maybe it might look like this. How many zeros does that have? Well, if I've drawn it well, that would have multiplicity 2 at that one point, multiplicity 1 at the other point, it would have 3 zeros. I think it's a question of orientation, but both things are positively oriented. And that's the theorem of Hopf that I talked about. The theorem of Hopf says the number of zeros counted by orientation is the Euler number of the manifold. That's one wicked theorem. So in that sense, every vector field has the same number of zeros. You have to know what orientation means. And you have to say, okay, I have to move it so it's transverse in some reasonable way. I mean, if it, you know, your mother might say, okay, my mother was a math teacher, but she's pretty good at it. And so she might say, well, I'm going to give you a vector field, and you tell me, son, well, how many zeros does that have? Well, of course, that doesn't count, right? You move it in a homotopy class. You move it in a smooth way until at least you have a finite number of zeros. Then you count, and you get the Euler number of the manifold. That's a theorem. That's an example of a real theorem. That's the tangent bundle. Well, you don't get much of a Nobel Prize for that. But if you understood the tangent bundle, you'd get close. Probably. Certainly, you would get a position at Harvard if you understood the tangent bundle of every manifold. But actually, for me, if I were checking you, I would ask you about the cotangent bundle more. Again, a big warning, cotangent bundle and tangent bundle in interesting cases are almost never isomorphic. So, let's talk about the cotangent bundle. Well, your mother says, okay, it's a bundle, I got you. Here you are. It's a bundle over M. Each fiber is the dual space. It's the dual bundle of the tangent bundle. So each fiber is a dual space of the tangent bundle, so it's a dual space. Okay. And you have the dual frames. And that's good, that's a dual basis. And you have frame change, which is by Jacobi. I'm claiming this is really Jacobi, but I'm not, but as I told you, I'm probably wrong. This is frame change. That's the structure group. And then you have sections. You're going to get tired of my picture. I only have one picture, the zero section. My statement of the Hopf theorem was, of course, only true in the compact case. I was thinking of compact examples. And you have sections here. I don't know, let's make one slightly different. That's a section, S. Remember, section is a mapping into there, smooth mapping, which goes in there. So that goes, this point goes to some point in the fiber above it. You're not allowed, you would be, you know, if you're creative. So I'd say, you take this point, I don't care where you map it, but to be a section, here's the fiber above it. No, I better get another color. The fiber above it is let's say blue. Yeah, and to get a section, at every point you have to have a point in the fiber above it. I mean, you can't be creative and say, I'm going to map this point to this fiber over here. That is not a section. You see what I'm saying? That'd be crazy. A section means across. So that means the point here has to go right above it. Just say I take a knife and cut through there, then it's a section. Right? Quite often in German, you might learn a German word, Scheibe. So that means really, in some sense, Schnitt oder Scheibe, sagt man auf Deutsch. So these words are really Schnitt, slice of bread. Yeah. Okay, so that's a section. And a section here, of course, in local coordinates, in the local frame, a section here, just like a section here, is equal to a linear combination of functions d x alpha I. Well, we know what the sections are here. The sections here, we know, are things of this type. These are one form. So the sections of the cotangent bundle, we know already a notation for that. I call them E1. These things are called one form. Well, already you got your job at Harvard, and the Harvard is pretty tough atmosphere there in the United States, you know, in Boston. But maybe you'd like to be professor at the Institute of Advanced Study. There you don't have to teach. For me, I love to teach, as you know, so it's a disadvantage, so I don't want a professor. But if you want a better position than Harvard, then you have to go there, so you have to understand more. So that means you should understand a lot more. You should ask your mother what she thinks about this idea of the following. Let's understand a lot more. Well, I understood that. A lot more at once. That would be really exciting if we could understand this. I almost got exhausted writing it. Well, what did I do? I had the tangent bundle, and I took the full tensor algebra of the tangent bundle. That means I replace every fiber by the full tensor algebra. Yeah? Now this is already infinite dimensional. I'm getting nervous, but at least it's formally no problem. Okay? I tensor that with the full tensor product of the cotangent bundle. That's equally infinite dimensional. That's really a big deal. On the other hand, if you're a little bit conservative, let's just replace this by the k-fold tensor product of the tangent bundle times the L-fold tangent product of the cotangent bundle. That says you're willing only to go up to, you only just, right? So inside this astronomical tensor product bundle, you have the k tensors from the tangent side and the L tensors from the cotangent side. Right? And you can multiply these things, and that's a z times z gradient. Well, what is a section here? Here's this basis. What is a frame? It's going to make me tired to write it, so I'm going to write Fij. I'm going to write Fij alpha. So alpha is indicating always, in my case, that we are using the coordinates alpha. Dxi alpha tensor ddx, excuse me, x alpha j. Now what does that mean? That means what you think it means, right? I mean, I'm summing I and j. When I write them as an index, that is always a multi-index. Okay? That means I1 through I, in this case, k. Okay? Over length k multi-index. I mean here sum. And I mean here the length of I should be k, and the length of j should be L. Right? And I mean here the tensor product of ddx alpha I1 through ddx alpha I k, running over all indices, and this is an example of, in a local frame, a section. Now I guarantee you these things come up in mathematics. Okay, and I guarantee you, if you understood all higher order bundles of this type, don't forget, if you understand these kind of bundles, you should understand something simpler. You should understand the k-fold, for example, the k-fold symmetric product of the tangent bundle. You should understand the full exterior algebra of the cotangent bundle. Or even simpler, the k-fold Grassmann algebra bundle of the cotangent bundle, etc., etc., etc. So I claim all of the structure of the manifold, all. If you understood all of this in the right way, you would understand the manifold completely, I'm sure. Okay? And I'm sure nobody understands this stuff in the right way. All of it. We understand some of it. Okay? Let me give you an example. You've done it in your homework a little bit. As an example, let M be the two-sphere, the two-dimensional sphere. You've done this as a home. So M is a two-sphere. The tangent bundle of the two-sphere. In the homework, with help, you prove the following proposition. This tangent bundle of the two-sphere is non-trivial. And this has consequences. This has deep consequences. The tangent bundle of the two-sphere is non-trivial. Right? Right? This is a homework exercise. That means this people make funny, when they don't understand something, they write a little story about it. It says, you can't comb something, what is it? You can't comb something about your hair. In my case, I have no hair. So somebody like Latif, who has a lot of hair, but his head's not a sphere. You have his nose coming out and so on, so it doesn't count. Highly non-trivial topology. Look at the mouth and nose and so on. So, yeah, okay, you have I've heard it, a billiard ball. People talk about a billiard ball. Yeah, you have, right, hair on a billiard ball. You can't comb it so that, I don't know, there's some word, you know, it doesn't have a non-vanishing vector field. Right? Two-sphere does not have a non-vanishing vector field. Isn't that terrific? That says a lot about the two-sphere. The three-sphere is, in fact, SU2. We've talked about that. SU2 has all of these fields that come from the group. It has a huge number of vector fields, right? Etc. S4 has no vector fields that don't vanish, etc. Okay, the reason it's very important, if you have a Lorentz manifold, up to a finite covering, you have a vector field on it which doesn't vanish. That's a big, big obstruction to a manifold being a Lorentz manifold. But these are all statements about the tangent bundle. So if you understand the tangent bundle, the cotangent bundle, the second wedge product of the cotangent bundle, we will spend 2 or 3 weeks on that in a minute. So wedge 2 of the cotangent bundle we will talk about. This is fundamental. Yeah, this is fundamental. If you understood all of that, you will get all prizes. Right? So go understand it. Okay. This is very, very important stuff. So this is, I know, a beginning course in the subject, but I think it's important for you to see what the fundamental objects in mathematics are. And the fundamental objects in mathematics are fiber bundles. Fundamental objects in geometry especially are vector bundles that are related to the tangent and cotangent bundle. Okay? This is called the full tensor algebra bundle of the manifold. Okay? You see them all the time in your physics courses because you see all these indices around. And what you're dealing with, of course, is this type. Right? So you're dealing with sections of these bundles. Quite often in elementary contexts, the manifold under consideration is a vector space or something like this. And therefore you can write these things globally in global coordinates. So you're dealing with just global things you can forget. But physicists have learned, not just yesterday, but not maybe in the 19th century, really how important it is to consider global geometry, not just local geometry. So it's very important to consider global things like that. Okay. Did I make enough propaganda for this site? I hope I made propaganda. Okay, I'm going to go to a very simple case. Absolutely fundamental case. Bundle. Namely, I'm going to the full exterior algebra bundle of the cotangent bundle. Now, let's just remember, this thing, it's a matter of just adding up all tensor products, all exterior products up to the dimension, because this stuff is alternating, and after dimension, it stops. Okay? Understand what I mean? If you have more than n alternating elements of the Grossman in a monomial in the Grossman algebra, two must be the same, and then you can alternate and put them together and they die. So you can only go to the dimension of the manifold. For me, the manifold is always n-dimensional. I don't know why, I'm sorry. Probably to be consistent, I should say m. So let's keep the dimension b. And this means the real dimension. Now, in a local frame, so let's say we have for this bundle, we will have, I will write it out long. So for, let's say, a local frame for the k-fold wedge product. So you will have these things. Now let's emphasize here what that is. Why did I take increasing order here? Any suggestions?
Because they're still symmetric, so that you can compute them.
We can always do it because they're skew symmetric, right? Yeah. And they should be different. I'm sure they what?
It would be zero.
Yeah, true, they're different. That's the reason I put increasing order. So I can always choose, starting out with a coordinate system, I can always choose as a frame, right? This is the basis here for the exterior algebra. Okay. So just to be emphasized, I often use Greek letters here. Omega in local coordinates will be some, well, I'll write it out long one time. Fi1 ik, depending on alpha, I1. That's a horrible thing, as you can imagine. how many terms you have there, right? Now, the action of the structure group GLNR on this thing is given by the action you think. It is A, say a matrix of some huge tensor. Well, it's a huge exterior algebra guy. Is just the diagonal action. So when you change variables, the structure group will be the same. G will be equal to GLNR, and the G alpha beta will be here. I hope you understand this now. It'll be just the same G alpha beta as before, but instead of acting on tangent vectors or cotangent vectors, it's acting on alternating tensors of this form, and so it's acting in a new way. It's acting here by this way. This is an incredibly complicated way. Can you imagine if you take a matrix that acts as usual on tangent vectors or cotangent vectors, and then you look at how it acts here. You take this basis, right? You saw the basis. It's already a terrible basis, right? You write this basis down, and you write the matrix of this base, of the operator in this basis. Let's see if I can get it. If I have, just for fun, how big, what are we dealing with here? I hope the dimension of the space.
It's a matrix 2 to the n by 2 to the n.
I think you're right. Maybe he's very fast with numbers. 2 to the n, but 2 to the n. Let's see if we can figure out why I said that. I think you're probably right. Wait a minute. The dimension, what am I talking about here? The dimension of the exterior algebra K-fold of Rn. Right? That's what we're dealing with. Are we dealing with that? So it's that basis, basically.
So it's n choose k.
Seems to me it's n choose k.
Oh, so you're not talking about the full.
He went all the way to the full thing. You get what me I did? I do that all the time too. He went to the whole thing. He loves this whole exterior algebra because it's really an algebra, right? You can multiply. I can't multiply if I stay there. So that's the dimension. This is the dimension of this one thing, right? It's completely clear. You have to take k things out of here and you put them in order, right? And now the dimension of the full exterior algebra is the sum of these things. So this is really, really big. And the action here, well, I mean, this is an endomorphism of a vector space of dimension n over k. So for example, if n is, I don't know if you people are fast, so n is 10 and k is 4. Let's just have fun, see what that is. That's 10 times 11 times 9 times 8 divided by 4 times 3 times 2 times 1. What is that? 6? I don't know what the heck's going on here. So
how did you get 11 there?
That's 33.
No, how did you get 11 in there?
I don't know.
10.
Boy, I went up instead of down. Okay, that's great. I wanted to be big. I wanted to impress you people that I could go big. So this is 10. That's good. Hey, and this was 4 times 3 times. I was just checking if you're paying attention, right? So this is 3. This is gone. This is all right. That's not bad. That's 210. So it's a 210 dimensional vector space. Suddenly, I mean, it's not very big. You have, come on, you have a 10-dimensional manifold, and you're looking at the tensors of degree 4. That's the exterior algebra degree 4. It's only a 210-dimensional vector space. You have a representation of the group GLNR on this vector space, acting in this way on the basis. Yeah, you can have some fun and write down a matrix. Okay. So you can see this stuff is relevant. One, you believe me, this is really canonically associated. And two, it's not simple. Okay. Okay. Just for fun, let's have the easiest one. Let's look at the n-fold. N is the dimension of the manifold. So locally, the local frame here is dx1 alpha wedge. We only have one out. Do you agree it's one dimensional? It's the n-fold wedge product of something n-dimensional. So you have to have them all different, right? So it can only be one dimensional. Right. So that's great. So somehow you have the one wedge product. That's just n-dimensional. Then it starts getting big. You see it getting big in the middle, right? Bigger in the middle, and then getting smaller. Yeah, you see this somehow. We will understand this as Poincare duality. So you will see something here in a good way. In the middle is horrible, and the end is good. Now, what is change of frame? So, how does GLNR act on this? Well, I just wrote it down for you. A of such a thing well, it's a diagonal action. So it's A dx. Okay, so, well, there's only one basis element here, so it's some number. By the way, this number has to be character of A, so I'll write a character of A. But it has to be a homomorphism, easily seen to that, times this thing. Anybody know that number? How these things change?
Determinant?
Hmm?
Determinant?
Yeah. This is the definition of determinant. This is the definition of determinant. Okay. The n-fold, okay, exterior algebra of an n-dimensional vector space is one-dimensional, and the group GLN, of course, or the group of general linear transformations acts on that n-fold exterior algebra product diagonally. Is one-dimensional, so it acts by a number. Okay, this number, by the way, you can prove is unique. I mean, it's essentially unique. This is the definition of determinant. There are many definitions of determinant, but I think this is essentially the only good way to think about it geometrically. Okay.
So what geometric meaning does it have? Because
volume.
Yeah, but I mean, how could we understand or represent the volume in this way?
Let me explain. Okay. So, first of all, I will define this as determinant. Okay? And if you want to know how, oh yeah, there's Jacobs. So it always comes back to Jacobi. There's Jacobs rule for calculating a determinant, right? And what you can do it if you want. You can really have fun with it, right? I mean, you just write it down. Write this number down. Okay. Now. Probably next week, because I want to make sure you have this. I'm dealing here with fundamental concepts. I hope you understand. And I really, really want you very much to understand this stuff. So I want to go rather slowly. But I hope next week I will explain the following. First, for next week, I will introduce this notation. I can introduce it now. EK of X, K-fold wedge product of the cotangent bundle sections of a cotangent bundle, k-fold sections of a cotangent bundle in local coordinates look like that, right? That's what they are. This is the local trivialization. They are smooth functions times this basis, and the change of basis is given by the diagonal action of the transition functions, which are called G alpha beta, coming from the Jacobian. Or in this case, I claim Jacobian. Local coordinate. These elements here, omega, is by definition what we call a K-form. And maybe I should be much more precise. Pardon me. Let's call it a differential K-form. Differential K-form. Why this word? In that fiber, over that point, that is the space of multilinear K-forms. Right? Over one point, it's the space of multilinear K-forms on the tangent bundle. Let's repeat it. The tangent bundle, tangent vectors. Cotangent bundle, functions. Second exterior algebra is the alternating two forms on that. Third, the alternating three forms. Kth, the alternating kth forms on that. That's the first blackboard over there. You start with a vector space and get a vector bundle. A section is a smooth association of points to K-forms. So we call it a differential K-form. It's moving smoothly. Isn't that what that is? These are K-forms. Okay. We're coming now close to the second theorem of analysis. Integration of K-forms and what it means. Okay, and that will answer your question. So, what I'm going to explain next week, I hope, is K-forms were given by, now I'll leave it to you if you're religious. You can put here, you put here what you want. Yeah, but don't forget, we started with a manifold, have a tangent bundle, cotangent bundle, huge exterior stuff, alternating stuff. Nothing went inputted from there to there. We say that is canonically associated to the manifold, right? The word canon has with religion to do, at least in the Christian religion. That is, this was canonically given by blank, whoever you like to say blank is, to us to integrate. And this means to integrate over k-dimensional submanifolds. You've already experienced this. One forms. What did I do with one forms? Remember, I had a curve. I had a one form in the neighborhood of the curve, right? I pulled back the one form to the parameter space of the curve and I integrated. I got something like work, right? Okay. So now, if I pull back a top level form, so the biggest I can go is this n form, right? Right. That's integration theory over the manifold itself. The things you integrate over the manifold itself are n forms. Okay? That's it. Period. Okay? So, you're probably not happy with this explanation, but at least it's some preview of what's to come. One forms over curves, two forms over surfaces, three forms over whatever volumes are in the manifold, all the way up to the top dimension. Okay? So I want to introduce now, this is all more or less formal. if we have a common effort here, we'll all get prizes. We share the prize money. When we go out to eat, we can afford a decent glass of wine instead of cheap wine. So. The next topic, which will involve our attention for the remainder of the time today and next time, is what I call the Durham complex. Durham, needless to say, was a mathematician from Switzerland. Very fine man who understood geometry and its relation to analysis. I remember correctly, he was in Lausanne, professor. Well, let me just write it. I'll write some stuff on the board that has no meaning for you.
Correct.
Maybe it does, you'll be happy. My friends tell me it's better to get stuff on the board without any explanation whatsoever and then at least there's something there which we need to discuss, and what we need to discuss is the canonically associated manifold Durham complex. Okay. And you will see that the related so-called Durham cohomology is of fundamental importance for many, many geometric considerations. So this is the, now I'll spend the rest of the day just saying what these symbols mean. Okay, at least it's just a bunch of chalk. And no more than this, right now it's just chalk. Well, you all know what this is. This is the C infinity functions. So that's another word for the C infinity functions. Now it's bad, there's so many arrows here. This thing here is the smooth function. Okay. Now this thing here is the complex numbers. This is the complex numbers, and now what I'm going to do here, I'm going to assume that M is connected, just to make my life a little bit easier. These are the complex numbers. But, yeah.
I just got a question about the things you did before. Is it, so when you defined one forms, were they necessarily...
What was your last word? What kind of form? Volume forms?
No, we defined forms again here.
K forms.
K forms. So,
yeah.
Didn't you define them to be, as so the one forms were functions on the space of the C infinity, of vector fields.
Right.
Yeah.
So they are sections of the cotangent.
Why is it alternating there?
Huh?
Why do you put alternating?
What's an alternating one form? I mean, that's a convention. I mean...
No,
it's a reasonable question. What is a zero form, by the way? That's also a question. It's a similar question. So I mean by that, an alternating one form is just a one form. There's no condition.
Yeah, but when you continue to bigger dimension, you have to put alternating stuff there.
Yeah, because it makes sense then.
Oh,
but I thank you for that remark, because you don't have anything to alternate with. You try to alternate and you can't do it. And the same thing with zero forms. So zero forms are functions by assumption. Okay? One forms we've discussed. Okay? And now these higher, so I should have perhaps said it that way. And then the higher order forms are the alternating forms, and that's it. Thank you. Okay? Now let's get back to these words here. So recall, I'm going to talk about the complex numbers for a minute. Recall, if d of a function is identically 0, remember, it can happen. Right? This means that f is locally constant. That means on every component of the manifold, it's constant. You understand? If in local coordinates, if d is 0, that means all of the partial derivatives are 0, right? That means the function, the gradient of the function is identically 0, right? So that means the function is constant locally. But maybe you're talking about over there in Delmenhorst or out there in Oldenburg or something like Hamburg. These are different places, right? It could be another constant on the other. It could be 1 on this thing and 2 on that. But I mean, d doesn't know the difference. So, but if it's connected, it is constant.
It is globally constant.
Globally constant. That is the definition of connected, by the way. Every locally constant function is globally constant. That's the definition of connected. Okay. So this is the complex numbers, but I'm viewing the complex numbers as functions. So I'm viewing them as constant functions. And now to the symbolism here. This is not symbolism in the sense of, it's notation. This symbol, I don't know if you have experience with such symbols, means that I've realized C as here. This means that this mapping isn't, I write it here maybe as an I, this mapping is an injection. This is what this symbol means. This means I is an injection. That's the first piece of symbolism. And now let's have some fun. What on earth does this mean? Well, it means here, for someplace in the middle there, I don't know where it is, you have a map from A to B and it's called D. Okay? You don't mind, do you? I map from A to B and I call it D. Then I have a map from B to C and I call it also D. Now let's see here. We do have a map here from functions to one forms. Right? We defined it. F goes to DF. Okay? What I want to do is continue that and get a map from one forms to two forms. And then from two forms to three forms. And from three forms to four forms, etc. I want to differentiate functions, get a one form. Differentiate one forms, get a two form. Differentiate two forms, get a three form, and so on. I want to differentiate forms and go to higher order. Right? Right? That's what I want to do. That's what this means. I want to go from, well, constant functions here, take D, I get a one form, take D, I get a two form, take D, I get a three form, take D, etc. I get an N form, and there are no more, so it stops. I go to 0. I just stop. Good, we have time to explain a little bit more. Okay. So far I have defined, this is okay. So let me here put the, maybe red, you can read it easily. This is easy to see what this is. I just told you the constants go in here just as constant functions. And now I take D of a one form and I got a two form. And the question is now, what is D of a one form? What is D of a two form? And so on. What is D of this thing?
So the first E is E0 then?
You're talking about this? No.
The first E that appears, is it E0 or?
If you would write down, yeah, of course, if we try to avoid too much notation, but if you need notation, I would agree completely with the notation D0, D1, D2.
No, I'm asking about
The C.
Function.
C infinity is E.
I'm not so sure. I'm not so sure. The way I view it is I have D0 from functions in one forms, and C is the kernel of that matter. That's the way I view it, and I don't think of that. It's just the injection of the kernel in there. Okay. Well, again, we have this thing. This is our sort of big goal in life, to understand something there. I have some room up there still. Let me just tell you what's going on. You have a sequence of vector bundles, in this case, the various exterior algebra bundles. And you wish to have of this type, and you wish to have, and you have an initial differential operator here. These things are modules over the functions, and you know what to do with functions. So you want to extend this so that these operators work well with respect to multiplication by functions. Okay? You agree, if I have a k form, I can multiply by a function, I get a k form. Right? It's just something going on in this vector space. Okay. So, I want to say this thing better work well with respect to the module structure. So if you multiply a form by a function, Leibniz rule should be valid. Remember Leibniz rule. D of f times g, okay, that would be multiplying a function by a function. The d of f times g was df g plus f dg. Okay. This is what you want. You want to extend these. You see, this is would be a definition of D on higher order forms with respect to, and we want, this is a property we want. Maybe let's call this property L for Leibniz. Right? We want this, and the word for this in mathematics is a connection on this vector bundle. You want to differentiate sections of a vector bundle, you don't know how, and you want to do it, and here's what we're doing. And this, a connection on a vector bundle must satisfy this Leibniz rule. This is the definition of a connection. It's a differential operator from one level to the higher level, satisfying Leibniz rule. But here, we require a dream. A dream. Let us call it D for dream. We require D composed with D equals Z. We want to extend the definition of D to the full de Rham sequence here. I will call it de Rham sequence. So the Leibniz rule is valid. And so the D composed with D is 0. That's wonderful if we can do it. If we cannot do this, the obstruction to doing this in geometry is called curvature. So if you have a connection, you extend the vector bundle sequence by a connection, and then you get something, maybe I write it something, you have some connection D, then you try and see what you happen, you get this. This second order term, the obstruction to D composed with D equals 0, is the curvature involved in this situation. In this case, I'm telling you, there's a way to do it with no curvature. It's because we have this wonderful Durand sequence with the cotangent bundle up to. So there is a unique way of doing it. Leibniz and the dream condition. There's a unique way of doing this. Okay. Decompose with D is 0. When decompose with D was 0, so you have a sequence of vector bundle, sequence then of their sections. Sequence of their sections. Decomposes D is 0, decomposes D is 0, decomposes D is 0, decomposes D is 0. That is called a complex. That's just a word. It's not like I'm in a psychiatric ward and I have a complex about being in bad shape because I'm 70 years or some, you know, I don't care. So I'm not in a, you may think I'm crazy, but I'm not in a psychiatric ward. I'm in a complex looking at some stupid psychiatrist. So this is called a complex in mathematics. It has nothing to do with complex numbers, just a complex. Okay? It means that decompose of D is 0. Let me just emphasize what the meaning of D composed with D equals 0. And now I will obey Mihai's suggestion. Obey is a little bit too strong for me, I'm sorry. But let's see here, let's go up to some place, the qth, I don't know, the qth level, and then the next one, the next one would be the qth plus 1 level. Okay? It means, here's A, here's B, say here's the qth level Q, and here's C, here's the Q plus 1 level. It means, so the combination of this map is 0. So it means that you take something in A, and you take it over there with DQ, now you're in B, and now you hit it again with DQ plus 1, and you get 0. It says that this thing is annihilated by DQ plus 1. So the meaning is, this is D, so I'll write it out long again, D plus 1 composed with DQ equals 0 means that the image of DQ is contained in the kernel of DQ plus 1. That's what it means. I mean, it's just formal, right? That's what it means.
But here it means like B, the space of B is much bigger than space.
Possibly, absolutely, absolutely. So that's right. So let's go with what you were saying. We're someplace in here. You're looking at the image here is something, right? Could be very small. Okay, but it's contained in the kernel here.
But the spaces are getting smaller after the middle. The spaces are getting smaller after the middle.
Yeah, but I was talking about images and kernels with him compared to the big space. But at the end, of course, they're getting very small. Yeah, I agree completely.
So it's hard to create them in the end.
Okay. So let's talk. This is really getting to be interesting mathematics now. This is not just fiddling around. So at the end, as you say, the last space is one-dimensional, right? So, and D of the last space goes to 0. So there's no condition, I mean, right? So the question is, you see what I'm saying? There's no condition on the last space, right? Now, if you really want to have some fun, then...
so in the end, these maps will definitely not be injective, will they?
No, this map is... No, certainly not injective.
In the beginning, they are. Are they in the beginning?
Well, this first map is injective, right? Basically. The only thing that happens here just kills the constants, right? Kills the constants. So as we've gotten onto this, let me just let you have some fun when you go home tonight and wake up at 3 in the morning and want to do some computation. The qth Durand cohomology This is what it's all about. The Q-theorem cohomology is a kernel of dq, let me emphasize, try to write this so you can see that. dq from Q forms to Q plus 1 forms over the image of dq minus 1 from Q minus 1 forms to Q.
So that's quotient space. That's a quotient space?
That's a quotient space. So as you've all been seeing here, these spaces are infinite dimensional. But in any reasonable situation, these spaces are finite dimensional. Okay?
What spaces are not infinite dimensional?
All these spaces of differential forms. I mean, you can imagine. I mean, they're modules over the continuous smooth functions, right?
Yeah, but I mean, if you fix Q, then here.
What?
I mean, if you fix Q, each space is here, then I'm finite dimensional. You mean the whole space of the...
Where are you now? Start where you are.
Yeah, this,
This is good stuff.
I didn't find any space which is infinite dimensional.
Yes, you did. Look, the space of one forms on a manifold, the space of functions is infinite dimensional. The space of one forms is infinite dimensional. The proof that it's infinite dimensional is it's a module over the smooth function. So you have all those smooth functions you can hit forms with to make independent functions. These spaces are huge. Okay? And then you ask the cohomology question. The cohomology question is given something in the kernel, does it lie in the image? This is the cohomology question. So we have no experience. You have no experience yet. We will have great experience in the next day or two. It's really fun with the cohomology question, but at least you can understand the question. Given something in the kernel, is it in the image? If something is supposed to be in the image, it has to be in the kernel. You get it? It has to be in the kernel. Okay? Now, if you understand this, then you understand a lot of the stuff that goes on in basic mechanics. So I repeat it. I think Professor Schubert will agree. The curl and rotation and all of these things, these are all words that are important, right? You ask whether something is the curl of something, or and so on. Right? Right? Now, let's look at it at one forms. Right? The kernel of D1 from E1 to E2 divided by the image of D0 from E0 functions to forms. The cohomology question is, you know it from your elementary calculus course. These are the closed one form. And these are the exact one form. Right? The cohomology question is, given a closed one form, is it exact? Given something upstairs, does it get killed in this quotient? Given a closed one form, is it exact? Closed means that. Right? Closed means that. You know what it means in terms of the coefficients? I hope you had some experience. So the one form is this. What does it mean that it's closed? I mean, a condition for being exact. Do you learn about this stuff? I don't know.
The condition for being exact, I know, but...
Yeah. What is the condition? Yeah, what do you know?
For the condition for being exact is df dy is dg dx.
Good. So this equals df means that f is equal to the partial derivative of f with respect to x, and g is equal to the partial derivative of f with respect to y, right? That's what I think that's what you were saying, right? That's the meaning of this exact. Is every one form exact? Why not?
Because if f is a smooth function, then fy should be equal to gx.
That's exactly right. It better satisfy some additional condition, right? This additional condition, necessary condition, is that it's closed. You just stated the necessary condition that it's closed. So closed means it's in the kernel of the D operator, and you just stated it. So it's necessary to be exact. It's necessary to be in the kernel, but it's not sufficient. I hope you know that. And the obstruction to being sufficient is topological. Okay? That means kernel divided by image is a topological obstruction to solving this differential equation. The differential equation is here. The differential equation is an overdetermined system of differential equations, and you can never solve such things unless you have additional conditions. Well, the additional conditions are what we've been talking about, to be in the kernel of the next operator. Okay. However, given something in the kernel, you're interested if it's exact, if it's an image or not. So you look at this quotient. This quotient is called the Ram cohomology of that level. Okay. Okay. It is an incredibly beautiful mapping from the geometry of the manifold into the theory of differential equations. I think it's incredibly beautiful. And it comes from extending the D operator, as we will do tomorrow, to have these two properties, Leibniz, and that's the connection property, and here is the connection that it has no curvature. These two properties, it's unique, it has a unique extension to give you the de Rham complex, which gives you the de Rham cohomology, which tells you a tremendous amount of math. Yeah.
I have a question. If you are finished, I have a question.
Yeah, sure.
You said that these two spaces, the kernel and the events, are of very big dimension.
Yes.
But what if we consider? Can we consider them as vector spaces over the smooth functions? Like, and then at least
They are not modules. You see, if you have something in the kernel, it's Leibniz rule. So if you have f times, say omega, look at Leibniz rule, it's someplace here. And it's good that you asked this question, terrific question. You have something in the kernel, you hit it with I like your idea, trying to look at it as a dimension as a module. But something in the kernel, you hit it with a function, take d of it, you get two terms because it's Leibniz rule. Now this gets killed because it's in the kernel, but you can't do anything about that. But I think it's a good way to think. But it is very, very typical that you have these huge spaces, but then you cut down by these kernel image things and get finite dimensional spaces. Theorem for a compact manifold, all of these spaces are finite dimensional vector spaces. And their dimensions are called Betti numbers of the manifold, and they give you a tremendous amount of information about the manifold. Okay? You can cut down, let me just say even more for people who are really interested, you would like to take good representatives of these equivalence classes, right? I mean, you have a quotient, you would like to have a beautiful representative. Right? The fractions 1/2, 2/4, 3/6, and so on, you would like to take 1/2 as a representative, right? And there's a theory to how to take good representatives of these things, using a metric on the manifold. So-called harmonic representative. Well, we should quit now. I've gone over, but we'll go on tomorrow. It's beautiful thing.